Hi student, today I am going to discuss about the numerical optimizations. Mainly, in this I split it into two modules where I'll talk about unconstant optimizations that includes the line search and task region methods. So I don't talk much about the task region, but mainly I'll talk about the line search methods such as the steepest descent method and Newton's method and quasi-Newton's method, where the first module I will talk about the steepest descent methods and with the few preliminary introduction about the methods itself and its application in R, how to implement the steepest descent method or gradient method in R, how to implement this, how if you have a function, how do you optimize that function through that method in R. Mainly in the first module I will show you how directly you can program the methods in R and get the estimate through steepest descent optimization method. Fundamental of unconstant optimization. All algorithms for unconstant minimization require the user to supply a starting point, which we usually denote by x0. Beginning at x0, optimization algorithm generate a sequence of iterates from xk for k0 to infinity that terminate when either no more progress can be made or when it seems that a solution point has been approximated with sufficient accuracy. In deciding how to move from one iterate xk to the next, the algorithm use information about the function f at xk and possibly also information from earlier iterates, say x0, x1 or xk minus 1. They use this information to find a new iterate xk plus 1 with a lower function value than xk. There are two fundamental strategies for moving from the current point xk to a new iterate xk plus 1. The first one is the line search. In the line search strategy, the algorithm chooses a direction pk and the searches along this direction from current iterate xk for a new iterate with a lower function value. The distance to move along pk can be found by approximately solving the following one-dimensional minimization problem to find a step length alpha. There is a minimum of fxk plus alpha pk where alpha greater than 0. And second one is the trust region. In trust region, the information gathered about f is used to construct a model function mk whose behavior near the current point xk is similar to that of actual objective function f. Because the model mk may not be a good approximation of f when x is far from xk, we restrict the search for a minimizer of mk to some region around xk. In other words, we find the candidate step p by approximately solving the following sub-problems, say minimum of mk xk plus p of p, where xk plus p lies inside the trust region. So let's learn about in details line search methods. So each iteration of line search method computes a search direction pk and then decides how far to move along that direction. So the iteration is given by xk plus 1 plus xk plus alpha k pk, where the positive scalar alpha k is called the step length. The success of a line search method depends on effective choices of both the direction pk and the step length alpha k. Most line search algorithms require pk to be a descent direction, one for which p prime delta fk less than 0, because this property guarantees that the function f can be reduced along this direction. Moreover, the search direction often has the form pk equals to minus bk inverse delta fk, where bk is a symmetric and non-singular matrix. The more common line search methods are steepest descent, Newton's method, and quasi-Newton methods. In steepest descent method, bk is simply the identity matrix I. In Newton methods, bk is exactly the Hessian delta square fxk, and in quasi-Newton method, bk is an approximation to the Hessian that is updated at every iteration by means of low rank formula. The steepest descent method implementation in R. Suppose you want to minimize the function, very simple function I am taking here, say fx equals to 1.2 into x minus 2 whole square plus 3.2. So this is a very simple function. Let us try to implement by the minimization process by steepest descent method. And basic calculus, but you can easily, from this function you can easily apply minimization methods to get the solution, and that we can compare with the steepest descent method. So that's why I took a very simple example here. The basic calculus requires that we find the first derivative and solve for the value x such that f prime x equals to 0. So this is easy enough to do f prime x equals to 2 into 1.2 into x minus 2, and it's easy to see that a value of 2 satisfying x prime x equals to 0. Given that second order conditions hold, this is a minimum. It's not always the case that we would get a function so easy to work with, and in many cases we may need to numerically estimate the value that minimize the function. So steepest descent or gradient descent offer a way to do this. The gradient descent algorithm can be summarized as follows: repeat until converge the following, that is x n plus 1 equals to xn minus alpha delta fxn, where delta fx would be the derivatives we calculate above the function at hand, and alpha is the learning rate. These can easily be implemented R. Say in R, write x, define one variable xk as a sequence, that is create some values, a sequence from 0 to 4 of length 20, and the total length of the array would be 20, and you will get a real number from 0 to 4. Then define the function we want to optimize. So our function that was 1.2 into x minus 2 whole square plus 3.2. So we will define a function, say f is a function, pass by value is x, and then 1.2 into x minus 2 square plus 3.2, and this is the function. Just passing the value of x, you will get the value of the function. So if I plot this function through simple plot command, so we plot x's fx's against x's, and then you will get the plot like this. The calculate and the steepest descent method, to calculate the gradient df by dx. The gradient of the function that I define is say 1.2 into 2 into x minus 2. So same way we will define a function in R that is called grad. The name of the function is grad, and the argument that we are passing through is x. So 1.2 into 2 into x minus 2. So this is the function that will give you the gradient value once you give the x argument. So because df by dx is actually 2.4, that is 1.2 into 2, that is 2.4 into x minus 2. If x equals to 2, then easily we can see that there is a solution x equals to 2, because 2.2 into 2 minus 2 equals to 0. The actual solution we will approximate with gradient descent method is x equals to 2 as depicted in the plot below. So let the plot, earlier plot, what we can do, we can draw this following lines at x equals to 2, where the solution is, that x equals to 2 is the actual solution. So that dotted red line, vertical dotted red line indicates the solution of the function. And the gradient descent method, let's start with an initial value, as I told earlier that it starts with an initial value. The initial value is say 0.1, and start x values and y values for graphic purpose. The initial value say x trace is the x value and f trace is say fx, the function value. The learning rate alpha, the step factor equals to say 0.6. So alpha is 0.6 we assume. Now the gradient descent update we can do here, like use a for loop, and for step 1 to 100, and then x equals to x minus step factor into gradient, that for already that alpha into delta fx that was given. This is x minus step factor, alpha instead of alpha here it is step factor into gradient of x, and then update the x trace as c x trace comma x, and update the value of function f trace is c f trace comma fx. This function after running 100 times it will create two arrays of length 100, one for x, another for the functional value. So that might be useful for update the plots. If you see the plots, then what we can do in the previous plot, we can just get a line of f trace against x trace, and we can use the type equals to both to indicate where the points are, and both line and points if you do, then you will see that gradually it converged at 2. So the solution is true. So if you just print x from this return of x, that if you print x, then you will get actually 2. So we started with 0.8, but we ended with 2. So this is the solution of the gradient descent method of that particular functions. So I use very simple function to compare how it's work, but in reality we apply gradient descent method where this kind of quite complicated formula where it's not easy to get the second derivatives from the function. Now the regression via gradient descent. So in a linear regression equation, as in vector format, if you write vector matrix of y equals to x prime theta, that is the h theta x say, and the generalized cost function would be j theta. Here if you would convert in terms of cost function, that is 1 by 2m sum over I equals to 1 to n h theta xi minus yi whole square. And generalized gradient descent algorithm would be then, while not converge, for j temp j equals to theta j minus alpha dj theta by del theta, and that is theta equals to temp 0, temp 1 dot temp n. So and del of del j theta by del theta equals to 1 by m, I equals to 1 to m, h theta xi minus yi into xji. So this is the basic algorithm when you are using gradient descent method to get the estimate of a simple linear regression. So let's implication in R. So let's create a 2 columns X matrix, as X is 1 1 1 1 1, and then X1 is 1 2 3 4 5. So X as a matrix, C bind as dot matrix, C bind X naught X1. Then create Y matrix of dependent variable as dot matrix C3 7 5 11 14, arbitrarily I entered, and then you will get the Y matrix, and M, then the length of Y is the, or row of Y, that is the length of Y in row equals to Y. Then implement this feature scaling, you can scale the data and then you can get the estimate. For scaling you can just x scale equals to x, and then x dot scale 2 equals to, you can use the scale function, or you from the fundamental standardization method you can use say x2 minus mean of x2 divided by standard deviation of x2. So this way you can scale the actual variable. X1 was not done because x1 was just the intercept 1 1 1 all 1, so no need of scaling. So the analytical results with matrix algebra, just you have to use the function solve with this x prime x. This is the R expression of that function x prime x into x prime y. So this is the multiplication, that matrix multiplication we solve it, that and that solution will come around 0.2 and 2.6, and for scale also same, is the scale x, that means trace of scale x scale into x scale into the x scale prime y. So it will be 8.0 and 4.1. So we can just simply fit the linear model to compare. So say LM function we use first for the unscaled variable, and this is the results of unscaled data with LM function, and estimate is around 2.6, x estimate is around 2.6, intercept is 0. So beta is 2.6, alpha is 0.20, and again for the scale value it is estimate is 8 and intercept is 8 and beta value is 4.11. So let's apply the gradient descent method and see whether it is comparable or not. To apply the gradient descent method, first of all you have to define the gradient function. Say grad, and this grade function we passing the three arguments x, y and the theta. So x matrix, y matrix and theta parameter. So the gradient equals to, already formula is there, the derivative of z theta, that is 1 by m into x prime into x prime x into theta prime minus y. So this equation already I discussed before, and then define the gradient descent update algorithm. Actual algorithm can be defined here. So here also I am defining a function for the update. So grade dot descent equals to function, the arguments that I am passing x and max int, and then theta equals to matrix C00, n row equals to 1, initialization of the parameter, all are 0, that theta equals to 0 as the initial value, and then alpha I assumed as 0.05, and for I equals to 1 to max int, how many times you will run the iteration is equals to theta minus alpha into gradient xy comma theta and return theta. So this is the gradient the gradient descent update algorithm. Once you run, you will get the results. So gradient descent x comma 1000, if I give, the solution is coming around 2.20 and 2.59, quite similar to the actual linear model fit results, and same for the scaling data, it is also quite similar to the actual fitting in data in LM function, where LM function you can see, recall that it is 0.2 and 2.6, and for scale 8 and 4.11, here it is saying 0.2 and 2.59, it is almost approximately 2.6, and here also 8 x0 and x1 is 4.11. So it is quite similar, it is generating the similar results that was supposed to be. And so I mean I just use a very simple examples. If you want, you can use any complicated function and can solve through gradient descent method in R. Only the actual derivation, the calculation part will change, but actual format or actual syntax of the algorithm you can make it unchanged. First things, as a whole, you have to define the gradient function, then you have to define another function that will update the gradient, or that once you call that function, that will give you the actual estimate of the parameter that you are looking for. So gradient descent method in R cost and convergence intuition. Typically we would iterate the algorithm above until the change in the cost function was extremely small value c. So c would be referred to as the set converge criteria. If c is not met after a given number of iteration, you can increase the iteration or change the learning rate alpha to speed up the convergence. Get results from gradient descent. Say beta equals to grade dot descent x 1000, and define the hypothesis function called h. So f theta xi beta 1 beta naught and beta 1. So then it will give you the hypothesis function. It will return the actual predicted y. So beta naught plus beta 1 into xi, and then define the cost function as t mat dot what dot vector 1 m for I equals to 1 to m, then cost ij equals to 1 by 2 m into hxi to beta 1 minus. This is the expression that we already discussed as a cost function, and the total cost is equals to column cost, and print the total cost, that is around coming 1.24. Save this as a cost of 1000, and cost 1000 is total cost. Now changing the iteration to 1001 and compute the cost 1001. So again I can compute the cost 1001 by this, and does this differ meet your convergence criteria, and if you get the difference, then it would be 1.5 into e to the power minus 11. If that is your criteria, then you can stop here, otherwise you can continue further. So that's all about the gradient descent methods and that implication in R. So in the first module of numerical optimization, we mainly focused on unconstant optimizations, where we learned the stiffest descent method here. That I took a very simple examples and I compared the estimate of the stiffest descent method and the normal optimization through differentiation, as well as, and I also took one simple linear model, or the simple linear regression, and I shown that how to estimate the parameter of that linear model by stiffest descent method. And I think these few programs that I have given might be helpful to implement any kind of function, optimization of any kind of functions in R in future after completion of this module.